frames, yes, but inside the bucket, you would be able.
A curved path to the east, even though great.
So I still don't understand what his point, or the point he was trying to make about Newton's bucket. I mean, okay, two different reference frames, yes, but inside the bucket, you would be able to feel it or at least measure a
That's what
centrifugal
Tim's
force.
just saying. That's what Tim's just saying. He's saying that you should be able. If you've ever been in one of these rides, he said, like, I agree. You feel it. Why would you feel it? How is it going to be different than you observing it from outside of the bucket? Well, outside you just see it spinning, and inside you feel the forces.
I just wanted to ask you, Zanick, like, about Coriolis. Like, if you really do believe that a sniper accounts for it, like, how do you reconcile that with hot air balloons?
Well, there you go. So now your mistakes are now coming forth, which I like now. This is good because we can talk about it. So it's almost like the question that was just asked by the other gentleman about the Coriolis and not moving. The sniper accounts for Coriolis for Yotvos. East and West will be accommodated by them. They know that's and Yotvos is a different type of effect than the Coriolis we're talking about earlier. We were actually traveling from a position on the Earth at a higher tangential velocity going to an area on the Earth northward that is at a lower tangential velocity. Hot air balloons are in the air that's actually attached to the Earth, roughly. So why would you? It's like the helicopter scenario we always heard for over 10 years now. But how does the helicopter just sit there and rotate when the Earth is, because the helicopter's in the air, and the air is roughly rotating with the Earth. In fact, on a calm day, it makes total sense because the air is not moving, so it's got to be moving at the same velocity as the tangential velocity as the Earth is. So why would a hot air balloon have any movement at all, deviating from its path as it travels, or hovering
bullets
rather?
in the wind too.
Pardon me?
Bullets in the wind too.
Yeah, get rid of all the other forces. Yeah, there's no question there's other forces involved. You're going through air. Air is not always still; it's moving. So now the question is: are those forces going to exceed what the Coriolis effect or what the Yotvos effect? You could have air moving upward from the surface. But
That's just my question is
after you remove all those forces, what's left? And so the Coriolis or Yotvos' effect is that
do
you
you
have to
really
consider.
think that snipers in combat think about this?
Depends how far the shot is.
Why do the spotter bring why do the sniper bring a spotter?
That was
You're probably
totally
right. A
irrelevant to the
lot of
question.
them are just using the sight. They're not calculating it out with a calculator. They know they're a mile away. If they're going to go for a mile shot, which is very unusual, but they can shot. What's the farthest shot that's on record?
All modern sniper teams use a ballistic computer. They have a Kestrel ballistic computer.
To answer your question, then, when we're on a gunboat and we're shooting a 16-inch diameter shell, 50 caliber across 25, 26 miles, Coriolis is in the friggin' instruction manual, and it's a chart that talks about exactly what you're contending. So why do you think they have that? If I'm shooting north, it's going to deviate 100 yards, 100 feet to the east. If I'm shooting south, going to the right as well. It's always going to the right, no matter which way you're shooting.
There's an interesting video of the USS New Jersey that's a museum ship, and you go into the firing solution room, and they said, and over here we have the firing solutions for ship to ship, which is only going 1,000 or 2,000 yards, and it's all mechanical. And they said over here on this side of the firing solution room is where we do the 25-mile from ship to land, and he states, he goes, this is where we calculate the curvature of the Earth and Coriolis for those firing solutions, because the hang time on those shells is over a minute and a half hang time to go those 25 miles.
Right.
We also did that in the computer in the M109, the 155 millimeter. I used to be in a recon unit, and we were trained to guide artillery fire, and we were shown how Coriolis is in the system firing solution, as you said,
right.
in the computer.
But it's so dramatic in the big shells and big cannons, and we are presenting to this guy the evidence to that the Navy does it. So we're answering his question. So are you in denial that they do that? That they know this shell, if they don't use Coriolis, will be off by 100 feet plus?
And like I said, the USS New Jersey, that firing computer and Coriolis effect and curvature effects, that's still existing. You can go look at that. And that's World War II. And the Germans, when they had their Paris gun, well, the maximum range you typically get from a 45-degree elevation angle. They found they can go a longer distance firing west by going to 50-degree because they got the longer hang time and the rotation of the Earth. Let the shell drop further west. Again, military big guns when you're dealing with these super hang times, as opposed to firing downrange, in line of sight of hundreds of yards.
It goes farther east when you shut it, right? Because the direction of spin.
As I recall, it was the Paris gun was shooting towards England, and they said they got increased range at 50-degree elevation because it gave them longer hang time.
Yeah, gave it longer hang time, yeah, because it's going against the spin of the Earth.
A good example, it was very practical, and a good example, well documented, because that was a big ass gun with a 100-mile range, whatever it is.
Yeah, today you when they do the firing solution, elevation of the target is tied into the Coriolis as well.
Right.
As you said, it depends a bit on the flight time, but also the elevation, because of course the lower elevation, the longer the flight time.
They have their whole chart: the most deviation going north or south, and almost zero deviation going east or west.
Oh, there's trig involved, yeah.
But the Yogos it's always a factor. That is a different calculation.
My response to all this would be that, one-offs or even a handful of instances would not be an indication necessarily of. I mean, it would be an indication of it, but it wouldn't be proof, is what I want to say. You'd need to do controlled shots, all the time.
They have a chart. It's chart. Okay. It's been declassified in the Navy. I posted that information many times here. You think they just
made it up?
Yeah.
The Paris gun.
I remember a guy telling me that he was on a Navy ship or whatever, and he said that they called it beyond the horizon targeting. So I don't doubt that they give these things great names and all that, And knowing what I know about trajectories of shooting out to about 1,000 yards, I can only imagine how complicated it is to actually shoot that far and try to be accurate. Because there's unless you can test the wind out that far, the only way to be able to know what's going on is to just lob things down there and see where it lands.
It's funny, they calculate. They have calm days.
Even those guys.
They can have calm days. We have days where the water is a mirror, like in San Francisco Bay. If you were shooting from San Jose or Milpitas out to the Bay Bridge, about 30 miles, 40 miles, you would be off by a couple hundred feet without looking at Coriolis. No wind. Wind's not doing anything. It's freaking calm the whole way there.
Have you ever shot 1,000 yards?
It's a real thing. And if you were on a gunboat or had a cannon there and wanted to make sure that was accurate, you'd plug in the direction you're shooting it, and then you put in your calculations about what angle you want to actually be with respect to the target.
And you mentioned
shot 1,000 yards.
Well, yeah, but you mentioned one-offs, like the German Paris gun. Okay, I'll give you that. That's a one-off. But on the USS New Jersey, their firing solution computer, which is expressly called out for curvature and Coriolis, is on every large battleship. Those aren't one-offs, and not just the U.S. Navy. So that's not one off. And as was
Dude,
pointed
Todd,
out, as was pointed out, as was
Okay.
pointed out, firing tables and the formulae for those trajectories is published.
No, I understand that. Yeah, absolutely. I bet it is published, dude. And you're gonna, like I said, you're gonna hate what I'm gonna say. But unless we were the programmers to put that in there, how the hell would we know that that's actually what it's doing?
Are
It's
you
the
saying the
same
military,
song and dance every time.
are you saying the military installed all these analog computers, had all these firing tables, teach it in all the weapons schools, but you don't know if they're actually doing it? Is that what you're saying?
So you got the picture there. I got one. Let's see if you understand what these actually are saying. This just talks about rotation, azimuth,
And that's another thing too. I actually
correction
don't
for
even necessarily
azimuthal,
deny that this occurs, that
correction to
there's this phenomenon that
listen.
happens. I can account for it with it,
This is compensate for the
an ether
rotation of the
win.
Earth. This is the Yovos ticket, and look at the deviations from pointing at the target, how it changes. Doesn't matter when you're talking about 2,000, 2,500 meters. So you already made that example, which was noted and not relevant because we're talking about things that are farther, where you can see what the effects are. And by the way, you start getting the long distance, 4,500 meters. Wow, look at that. You're talking 4 mils of change, but 0 mils at 1,600 or 4,800
I
north
guess
or south.
the real test would be,
Well, no, but can you please address that? Because this is
I'm
there.
sorry, go ahead.
You're at zero. You're 0 degrees latitude because there's a sheet for every latitude. This is at 0, and this is the azimuth of the tau in mils. What the deviations would be. So why is it at 4,500 meters? Why do we see this deviation go from 4 to 3.7 to 2.8 to 1.5 left, and then to 0, and then opposite as you continue this rotational azimuth? Can you explain that? Why they have this there? Why do you think they made this up, or it's just ignored, or it's just baloney?
Well, it's definitely not because the Earth is spinning,
Well, of course it is. It's because the Earth is curved and it's spinning.
Yeah, I don't necessarily think so, man.
Well, you may not think so,
It's
but that's
funny, yeah. Funny how this ties into like things like focal pendulum, the large weather patterns north and south of the equator.
yeah. How do you have this precession of this Foucault pendulum that is never precessing at the equator, but you can predict your latitude anywhere else on the Earth with a Foucault pendulum based on its precession rate?
I heard people argue this again, these same old arguments
Yeah,
time and
but you
time
can't.
again. We all
But it can't
know.
be. It's indisputable because you can go to France, and because you have a 33-hour rotation, this precession takes 33 hours, not 24. And at the North Pole, they say it's going to be 24, or South Pole 24. But we don't really have a Foucault pendulum there. But they've gotten pretty close to it by doing their experiments in that region. But these things are indisputable. They always work because of this effect, this rotational
Yeah, I
effect.
mean, as good as every university of some size on Earth has these, where
There's actually
where
live. There's
yeah,
live
where the
video of these
students do these
pendulums you can
tests.
watch. You can watch them spin right now. Probably go to France's university in France where they have that example in a museum or in a university, and you can see exactly what it's doing and see how it precesses based on its latitude.
I think this was debunked a long time ago, and I don't want to
Never
argue
debunked.
with you about it.
Ever. We've never
Debunk how?
debunked it ever. It's not debunk. It's not debunkable.
There's something
People try to
very
say it's true.
slight that happens, but it sure as hell isn't because the Earth is spinning, and it's
Then what is
definitely.
it? But
Why
then what
would
is it?
Then what is it? That's not even. That doesn't even make any sense, dude. It's the motion translated down from the sky is what it is.
No, that's not what's happening.
No.
Funny. What's that approach? Before he started getting a little more astute about what he was actually saying, he was actually saying, it's so actually really funny. I remember quoting him on this, and he always backed out of it. And then he said, "I never said that." And of course, we had the recording. Why does the focal pendulum precess one rotation every 24 hours up at the North Pole or South Pole, and why does it not precess at all at the equator? Can you understand? Tell me about your downward. What did you say? What was your explanation to it? Downward forces from the universe. I don't know. What did you? Something kind of nonsensical.
And
But tell me
rotates
how
the
that
other,
applies.
and precesses the other direction south of the equator.
Yeah.
Honestly been like 2 years since I really got into that, and what I'm remembering from it is that
Oh,
it's the same fictitious forces from the relativity nonsense.
it's not from relativity. What do you mean from relativity? You mean relative motion, or you're talking about Einsteinian
I wish I
general
had the
stuff?
memory some of these other guys do. I go through and I learn it, but after a couple of years, it gets a little
Oh, I
foggy.
get it. Well,
So
just walk. Well, then
in
you can
the
see, you can check
in,
your logic if you just walk me through what you're
in
saying.
relativity,
Why,
in
why
relativity,
does the
there's
precession change
yep,
directions below the equator, and it can predict your latitude there, and it also change directions as you go north, and you can detect your latitude in the northern hemisphere, and then only rotates in lockstep with the rotation of the Earth because, yeah, what it was saying, because the Earth is rotating underneath it. And
I kind
that's
of
what
lost you there.
they said.
I was trying to remember how to, yeah. Because Whitsitt said
So
it was
what you're
rotating.
saying is,
What?
yeah. So what you're saying, it's not the Earth rotating; it's something unknown which is causing
I, I could,
the
I,
precession.
I could equally just as well account for it by saying it's the same motion translated down that's rotating sun, the moon, and the stars. It's
What?
actually accounted for. It's accounted for in relativity by what they
What do you
call
mean
the
relativity? You mean
fictitious
like
forces.
Einsteinian relativity? Relative motion or relativity? What are you talking about?
Yeah, relative motion. See, that's what I was saying. Like this was something I was a little bit better at about 2 years ago, but I kind of, I
Bad or
don't
yeah,
know.
you
The
were bad
argument
then, you're
obviously went
bad,
by the
you're worse
wayside
now.
a little bit.
Go back and get your ducks in a row, and
Oh,
we'll come back and
definitely.
talk about it because it's a fascinating subject. It's very it's cool. It's physics, basic physics. Talk about it in grade school. Why not learn? Dummy up on it. We'll go over it because there's nothing you can say that I can imagine that will dispute the this use of this tool to detect the rotation of the Earth because of the basic principle of objects swinging from a pivot point and creating a plane of oscillation and how that plane will
Kind of
rotate.
can't wait. I kind of can't wait to explain all this again because maybe
Yeah,
there'll be
you should
some
do it.
new
It should be
ears that'll
motivating
hear
to
it
go
because
do it and
it's
try to
all
challenge it
old
again.
arguments.
And I'll
Old
get my old arguments
arguments.
as well that address these misunderstandings, and we'll have a little powwow about it
Yeah.
because it's if you understand why these things happen. And I wish I could remember what the what's it objection because it was actually classic, and I kept on saying, what are you talking about? I can't remember that. It's kind of very humorous. Um,
All right. I
the one point I
apologize
remember
that I
what.
can't come up with anything better at the moment right now, but I guess I'll leave you with this. I remember Robert Bennett talking about when he was learning in his physics class many years ago, and then they started talking about fictitious forces, and he says, "Look how I'm paying good money for to learn about fictitious forces."
Okay, so there's therein lies the problem. So do you know what a fictitious force is? Do you know how it's defined in physics?
Yeah, they're basically like extra or outside of what is relativity, and it's ad hoc to make it work, I guess, in
No,
layman's
not at
terms.
all. So I remember Toons had mentioned to you. Do you feel the force in the centrifuge when you're spinning around in that carnival ride? Do you feel yourself being pressed against the outer rim of this thing? That's because that's a fictitious force, but you still feel it. And why do you feel it? Still real, right?
I
You still feel it.
I, I
It's
like
a
to
fictitious.
call it
It's go on.
emergent force.
Well, fictitious force is fine. I mean, he doesn't like the word fictitious because it makes it sound like it's fake. It's just a word in physics that they use to describe, and I'll give you the answer. I'll give it to you right now. A fictitious force is a force without origin, and it's reference frame dependent. Now, just because it's reference frame dependent, and doesn't have an origin, like a centrifugal force, all pseudo forces, it doesn't mean they're not real. They don't try to use it just to rectify things they don't understand or try to make the equations work out. No, it's actually real. All they're talking
It's
about is a description of where that force originates, where it comes from, and uh, that it is reference frame dependent. It is dependent upon a reference frame.
I
it's a
think
net
that
of it's a
no, that's
net
great.
effect.
I think that's it.
It's
I
a net
think that
effect.
the
And
centrifuge
what you
is a
said,
really really good example because if it's not spinning, there's no centrifugal force. As you start spinning it, the faster you spin it, the stronger those emergent forces are, or fictitious forces. It's not that difficult to understand.
But they still are reference frame dependent, because if one of those planks that this thing was constructed with came loose, you'd fly out the backside, and your motion would be a tangent to the rotation in the direction that the tangential velocity of that outer rim. You'd fly out
Yeah.
exactly at a tangent, straight as an arrow, not turning. The only thing holding you in is that plank that you're leaning up against that's been nailed or welded to the rest of the planks. Another example is turning in your car. If you're in a race car, we're taking a big turn at old Auto Club Speedway, and I'm going down the bank turned, and you're in my passenger seat, and your seatbelt's not attached. You're pressed against that door, and the door opens up. Where do you go? You go flying out. That is centrifugal
that's
force.
where in Earth's orbit. That's where in Earth's orbit, where it's asymmetrical and it's not a perfect circle, there has
No,
to
in Earth
be.
orbit where
That's
there's
where
no
that
forces involved.
linear
There's no
part of
forces in Earth orbit.
relativity
It's
comes in.
free fall.
Where
It's complete free fall.
yeah,
Both the
free
Earth,
fall in a
Earth
straight line, like
a geodesic line, yes.
with no lined up with the North Pole, basically. Is that right?
We're talking about the Earth orbit around the Earth, or
Yeah. Which
Earth's
way
orbit
are we
around the
moving?
sun. Earth's orbit around the sun,
Yeah,
or something orbit around the Earth.
I don't know.
One more time. Earth's orbit around the sun, or something orbit around the Earth. They're in free fall. Even though they're making a turn, it's a geodesic. That's a little more involved to talk about, because now we're talking about a curved path with respect to someone on the Earth, but a straight path with regards to the forces.
That's a relativity is just totally off in the weeds, man.
Oh, if you jump off a building, why are you in free fall? Yet we can measure you accelerating to the ground. That's a paradox. True paradox.
And for
Unless
any
you
acceleration, you need a continuous force acting on the object.
right, yet we can prove there's no forces acting on the object that gets dropped. But why is it accelerating? And they say that the ground is accelerating upward to the object. And that blows the flat earthers' mind, because they can't accept that sometimes acceleration is not a change in speed, but a change in direction. And the whole thing about the bending warping of space-time is a change of direction. That's why
It blows the
Earth
flat
has-
earthers' mind. Yes, because the math is illogical, bro.
logical where. So then what
Real
causes
simple.
something? If it's illogical, you'd explain to me, why does something accelerate when I drop it off of a building? Why does it accelerate, but yet there's no forces acting on it?
Hey, man, it's just like old as time itself, man.
Just give me whatever you're explaining. People would say it's bending, warping, and space-time, but what do you think it's due to?
What do I think that it's due? Like, really, you
Yeah.
really want my honest opinion,
Yeah.
man?
Yeah. Give me your, use your imagination. What do you think could cause something to accelerate without a force behind it?
Field pressure mediation.
What? What does that mean?
That is an
Field
effect, though, isn't it?
pressure mediation.
What is
So-
pressure mediation? Why don't you
Field
throw
pressure
dielectric in while you're at
mediation.
it?
That's exactly how it's moving.
Why? How does pressure mediation work?
I mean, there are probably a lot of ways to illustrate it, man. I mean,
Oh, if there's any, if there's one, I'd like to hear it.
here's a good one for you. Do you know what a cymatic pattern is? like the sand on the plate.
Yeah.
You know why the sand gathers in certain areas and doesn't in others?
But there are forces involved.
Correct.
Maybe field pressure mediation.
No.
Yeah,
That
yeah. The
sounds like
there are forces, vibration forces.
that sounds like an Uncle Fester response. Pressure
Certainly what's
mediation.
going on, mister.
Uncle Fester told you this, right?
It's just a malformed question, dude. How can you have an effect without a force? You can't.
It could be a really ultra low frequency sound wave.
And that is a force, pressure
We
waves
are,
in the air.
you know,
No, dude, you don't have to grant them their claim that gravity's not a force. You don't have to grant that claim.
oh no, I'm just, he asked me literally what I thought gravity was, and I'm honestly giving him my answer, what I think it could be. I'm just saying I know.
He said
But it's
pressure
definitely
The
mediation.
question
some
was,
type of
how do you have
pressure wave.
acceleration? How do you have an acceleration without the force involved? That was the question.
I don't have to grant that. Why would you think that there isn't a
witness
force
it.
behind an effect?
You can witness it. Drop an object. You can and put it in a container where you can actually measure these forces in there, and it's all in free fall. There's no forces acting on it yet. We can measure it from a ground position. Measure that this object that's falling is actually accelerating, but yet inside there's no forces being measured. But yet we can measure it. We can see it accelerating. That's either a
From a
paradox
ground,
or
You're saying
there's a
that. Yeah,
reason.
you're just simply stating that there isn't a force because Einstein said that it wasn't a force, but it
no, you
most
can actually
definitely is a
measure it.
force.
You can measure it.
Yeah, you can measure the force. Absolutely,
No,
you can
you can
measure
measure
it.
there's not a force.
Nope, you can measure it because all you
You
need to
can't
do
measure
is wait for it to hit the
you can't measure
ground.
something that's not there.
we're
It's
always
there. You
referencing the
just
ground.
it's just
It's not
limited
there.
by your instrument is limited, right? So the accelerometer that you're using to measure it isn't going to be able to pick it up because it's limited in its engineering.
How would you suspect or how would you guess that you could actually develop some kind of tool to measure something that is not there?
No, you can measure it.
Give me a couple ideas of how that is possible. You're in free fall, and there's no difference between if you're in space floating, or you're being thrown off a building, other than air resistance drag. How do you
It's the thing is,
rectify the fact that you can't measure this? You can't. There's nothing there to tell you that you're accelerating, yet you are.
I have the
no.
answer.
Well, see,
I
it's
have
a
the
double.
answer.
You're double speaking. You're saying it's not accelerating, but it is accelerating. So
It's
which is it? Is
inertial.
it accelerating or not? Because if mass is accelerating, there has to be a force behind that
That's
acceleration.
why it's a paradox.
Logic itself necessitates that
No, but that's the
for
paradox.
every hold on, dude, hold on, bro. For every effect, right? There's a necessary antecedent. It's actually called a cause, right? To
Yes,
every effect,
in
there's a
Newtonian physics,
cause. The cause is synonymous with a force, right?
okay, you're
You
stuck in
can't have
Newtonian
an
physics.
effect without a
Let me know when
force.
you're done.
I'm done.
I keep on. Okay, so in Newtonian physics, you'd be right. That's why for years, and we still to this day still can apply pseudo forces in these scenarios and get correct answers, even with the knowledge of Einsteinian physics. These all can be explained, expressed in terms of each other as well. But no, this object that is falling is accelerating. You can actually visibly see and measure this second derivative of distance with respect to time, i.e., acceleration, can be measured. Yet inside that box, these objects are all free falling, and there's no forces acting on them. So you have to explain to me what kind of tool could you measure this required antecedent, as you said, of a force when there is measurements of no forces being involved in these falling objects. But we see
Is
them
that
just
due
accelerating.
to the forces sort of equalize?
Just because you can't pick up, right, the centrifugal force because there aren't any centrifugal forces acting upon the object because the object is basically at an equilibrium, right? It's reached a point where the accelerometer isn't going to pick it up, right? Because of
No,
the
not right.
downward vector. because of the downward vector.
No, there's
So
no vector.
it's like
There's no vector.
it's like
There's no
B.
force.
It's like B.
It's
Hold
in
on,
free
dude.
fall. It's inertial. It is
Oh,
stated to
dude.
be inertial. It is inertial. It is not accelerating nor turning.
It is accelerating. We can perceive it
No, it's not.
accelerating.
You measure it to not be accelerating or
It
turning.
is accelerating at 9.8 meters per second squared, dude. It's
Yes, but
most
there's no
definitely
forces acting on
accelerating
it.
towards
There's
the
no
ground.
forces. It's
So how is it
inertial.
accelerating? So how is it accelerating?
Well, because there's one theory that says it's passing through the warping and bending of space time. Its path is actually turning, even though its speed is not. Its path.
So there
through
is a
time
force.
is going forward, but with respect to the Earth, that space time is curved and it's curving toward the center of the Earth.
Yeah, so there is a force.
No, there's no. I just got to saying, well, there isn't a force. There is
Okay, so
absolutely no
why do you
force involved.
have? So why is the kinetic potential or the kinetic energy multiplied?
Why does it have kinetic energy? Why does it have potential energy when it's dropped off a building?
Not just why. Why is it multiplied? If there's no force behind the object, how come it's being multiplied? The kinetic
Why is it
force.
accelerating? Why is it accelerating? Is what you're saying?
Not just accelerating, the kinetic potential is multiplied
Kinetic
as it
potential.
accelerates,
That's
showing
what
you
acceleration means.
that there most definitely is a force.
It's
Yeah,
the second
yeah.
derivative of
So
distance with respect to
force
time.
equals mass times acceleration, right? Not only do we pick up acceleration, we also pick up the kinetic potential being multiplied. And then you
Only
want to
with respect-
deny not only that the mass is accelerating, that the force itself is being multiplied, and then say that there's no force acting upon it.
Well, you're
kinetic energy is
you're mixing up terms a little bit. Go ahead. Sorry.
Yeah. No, I mean, kinetic energy is how fast an object is moving and the mass of it.
With respect to the ground.
Yeah, or a surface of some sort.
Right. And so, yes, we know that it's accelerating when we look at it, and we can calculate by the moment it's dropped what that kinetic energy, this potential energy, which is when it's before it's dropped, is a potential energy, and it's always with respect to the ground. That's a given. And we drop it, and suddenly we know that object will release and exchange potential energy with kinetic energy until it hits, and it'll just the opposite will occur when it hits. That's a part of the paradox. Yeah, we are accelerating. We are increasing kinetic energy with respect to the ground. But why? Because the gravity is a pseudo force.
Oh my God, dude. See, the biggest indicator, the biggest indicator, right, that we're dealing with an actual force isn't just the fact that it's accelerating. That's one indicator. The second indicator is that the mass itself, right, when it's accelerating, the force is being multiplied, right? So when it hits the ground, the higher that you drop the object, the harder it's going to hit the ground. So you have two indicators that we can empirically observe with our senses and empirically measure with accurate detection, and we can measure the force being multiplied. Yet, you're telling me that I have to ignore both those indicators and
you
say
got
that
it
there's no
backward.
force acting upon it.
Well, you actually have it backward. You have the right idea, but here's going to blow your mind. I mean, you've probably heard this before. You're actually right. There's an acceleration, but guess what? It's not the object, because I told you already it's inertial. The ground is accelerating up to the object. That's why you have
No,
the
it's
impact.
not. The ground.
It's accelerating upward at
He's a
9
rising
meters per
earther?
second squared. Yes, it is.
Jesus Christ.
You can
now
prove that
they
by
have to
standing on a
resort to.
scale. Hold
They
on,
have
hold
to
on.
be.
I let you
All right.
speak. I didn't say a fucking word.
I'm sorry. Go ahead.
So you can stand on a scale and you can measure your acceleration. The acceleration of the ground. The ground is coming up at 9.8 meters per second squared. That's why you have a register. You know you're not moving. You can see it. But why is the ground going up? That's the normal force. Your pseudo force is going down because you are inertial if you're dropped. But when you're standing on the scale, there's a proper force pushing up on you. It's accelerating upward. The ground is accelerating upward.
No, it's definitely not accelerating upwards.
Why not?
I don't know why you would abandon reason and rationale just to keep your model afloat. It's kind of funny, dude. It's known as belief perseverance.
No,
you have to resort to rational understandings of things.
Irrational? How is it irrational? Because
it's the sunken cost. It's the sunken cost. Zanick has put so much into it. You can't turn back now.
all I have to
I'm not
do,
fully committed. I can't change
Zanick,
my mind
all I
now.
have to do to demonstrate that you're wrong
I'm
is
too
very
vested.
simple.
I'm too
You
vested in
you
this.
get a scale, right? You get a scale. You put it up against the wall and you lean on it, right? Just by simply leaning on it, or even push up against it with your arm and keep steady pressure on the scale. You're not moving. The scale's not moving, but guess what?
Two proper forces.
It registers a force by
Two
simply
proper
leaning on
forces,
it
yes.
or pushing it on it. Now, the scale itself isn't accelerating towards you. Instead, you are the one accelerating towards the scale. You are the one
You're not
pressing against the
accelerating. No,
scale,
no, 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 no.
causing it to register a weight. It's
No,
no
no, no, no.
different
You're
than when
almost
you're
had it there.
standing on the scale, right? When the scale is horizontal on the
Radius to
surface of the
reiterate.
ground. When you stand on the scale, your body itself is pressing down, right? You are accelerating down, causing the scale to register. Why would the earth be pushing up? Why would the earth be accelerating
I'm
up?
trying to
Why would
tell
you
you, you're
resort
not
to that
listening.
irrational stance? Go
I'll
ahead.
give you the answer. I'll give you the answer right here. Pushing against the wall, if the wall was to give way, it would then accelerate. Right now, you have two forces you have zero net force. You're leaning against the wall's leaning against you, pushing against you. Just like Newton says, two proper forces, no argument. However, when you're standing on a scale, a whole different paradigm is set up now. Because if that floor gave way, you would then accelerate at 9.8 meters per second downward to the lower floors, but you would be in free fall while you're doing it, not accelerate. No force is acting on you. The other scenario against the wall, you'd have to be continuing to push that wall. You'd have to continue to add force. You have to put a rocket engine on it to continue to accelerate. You would feel it. You'd feel G-forces the entire time you're accelerating laterally. You don't feel any G-forces when you're dropped. Don't you see the difference? Think about that. You already talked about it against the wall. Now you're talking about the scale. And you said why, and I'm trying to let you conceptualize what's going on. The wall scenario, if I'm going to continue to accelerate laterally like you're in a 911 turbo and you're going to accelerate to 60 miles an hour in 3 seconds, you have 1G pushing you in your seat. You feel that. But I drop you, same acceleration, you feel nothing. You see? So something has to give here. You have to understand there's something that either a paradox or there's an explanation. The explanation, as modern science accepts, is that the Earth is accelerating upward. That the free fall, you're inertial, and it's happening because space-time is bent, and it's bending down to the center of the Earth. There you go. Now your mind has been blown. I love your passion. I love your.
I gotta get back,
fight,
dude. I gotta
but
get back. I'm at another delivery, but listen, we'll continue with that.
All right, Bubba. Always a pleasure.
No, the resolution is that there just is a force that causes the falling, and
Why
an
don't you feel it?
accelerometer just can't pick it up because it's a limited device. Because the sensors are moving at the same speed as they're all free falling together, because everything free falls together. So that's what resolves it. You don't need to have the Earth moving up. You just do have a force when it's falling. That's what gravity is.
Well, how can we feel it if you're laterally traveling, we feel it, you're pressed into your seat accelerating, but when we're dropped out of a building, you feel like nothing. Why does those two things, which are exactly the same acceleration, why do they feel so different? Are we also unable to measure the force? But we can. We know the difference. We can say, hey, laterally I felt this friggin', my face was pushing backward, my mommy, my pigtails are too tight. But when I dropped off a building, everything's relaxed and everything's floating. Things in my stomach are floating, I'm floating, my hair is floating. Water, saliva in my mouth is floating. Everything's floating.
Yeah, it's because the XY axis is different than the XZ axis. Vertical is different than horizontal. Well, there's only a free fall in the vertical matrix. You don't free fall sideways. You free fall vertically.
But if I wanted to show you the acceleration laterally, we feel it. When we do the acceleration vertically, we don't feel it.
When you're
You
dropping,
said it was
yeah.
an instrument.
Yeah, because in order to horizontally move, you always have to push in some way. But to free fall, you just have to let go, and everything free falls together. So the accelerometer is free falling. The sensors in the accelerometer that would normally be pushing against each other when you go horizontal are just both free falling together. That's why it's not registering something. It doesn't mean that there's nothing going on. There's not an acceleration going on. There is. It's just not able to pick it up. But you're using that assumption that there isn't one to then have to say the Earth is moving up, which just leads to a whole faulty conclusion or faulty outcome.
Well, how come we don't feel anything? Like you say, maybe the sensors can't pick it up because everything's falling in unison. You said, but why can't we feel any acceleration? We can't feel acceleration. We can only see
You
it.
do. No, we do. Have you ever
No,
jumped
you
off
won't.
have you ever gone cliff jumping?
Of course. Who do you think you're talking to?
What's the tallest you jumped off? I did 100 feet once.
I've been 75 feet a few times, but yeah.
I think we
Probably
measured it. It
100.
was like 90, 95 or so, like almost 100. Dude,
Dude,
it is.
90. Dude, are you crazy?
Yes, it was crazy, and I was crazy to do it. We
It hurts
filmed
your
it too.
feet. We had to jump. We
Dude.
had to jump even at 75 feet where we weren't diving. We were just doing backflips. But when you land, man, your feet. First time we did it, man, your feet were hurt for like the whole day. So we started
Oh
jumping
yeah.
with. We used to jump with flops on.
You
Now these
gotta
days they're
wear.
doing belly. People are doing belly flops at that height now. I don't know how they do that. I've always wanted to try it, but I figured if I did it, I'd probably get knocked out and die.
No, it's not a belly flop. It's called like death diving.
Right.
It's not really a belly flop. It's
Well,
like
no,
the
you got your
opposite
feet,
of a
your
belly
your feet,
flop.
and your hands together in front of you, which break the surface tension. But I can't
Yeah, they
imagine actually
say.
doing that.
I know, me neither. But they say it's actually better. Because, dude, when you like doing like 100 feet like that, or like you said, 75, because there's one area of cliffs. There's like several. There's like the 100. There's a 70, 50. You know, there's several of them.
Right.
And dude, I couldn't imagine doing that death diving thing. But they say it actually is a better impact because, yeah, when you do it like just feet down. Like, remember those aqua socks back in the 90s? Like, we had to wear
Oh,
like
yeah.
aqua socks. Like, you got to wear something because
Yeah.
it will smack the bottom of your feet.
But
It's
don't you
intense.
think like I guess your hands and your feet because they're kind of pointed now, and it's not a flat surface. Break up the water. Then by the time your face hits it, it's already kind of turbulent. I guess that's a theory. I kind of believe it, but I don't know if I'd risk my face on that concept. I'd end up doing it and probably end up getting knocked out. To say at my age now, I'm just not. I do other things that are pretty death defying, but not. I can't get myself to do that. I want to, but I just can't do it.
Yeah, but dude, they do it insanely where they jump off massive and they're flipping and turning, and then right at the end they just go into that
Boom.
pose.
Yeah, I know. It's
Yeah.
crazy. It's insane.
It must be better. Like, I've never tried that because that's kind of a newer thing.
I wish I would have been a thing back when I was younger because I would have definitely been doing that. That would have been fun.
Dude, you really want to do that though? You want to be 100 feet
No,
or whatever,
not
75,
100 feet.
whirling towards the ground and then go into that, like, basically it's like a, what is that kind of position? Yeah, like, you know, if you were crawling, basically.
Pike, like a pike position.
It's like crawling, but your feet are pointed down, or like a
Pike. Your feet and your hands are in front of you, so that they're not flat though. And then when they hit, they kind of break up. They kind of like a knife into the water, get the water moving, and then it becomes just. By the time your face hits it, it's all kind of just bubbles.
I guess so. I know it's like a downward dog in yoga, downward dog
Yeah.
pose.
Exactly. Yeah.
But anyways, but the thing is, dude, when you cliff jump, you can feel the acceleration. I mean, you just when you first launch off, you know, let's say you run, because I like to do it when you're like a running jump. So you do a running jump and you go run, and you do your last leg, you know, extension off the rock, and now you're falling. And at the beginning, it's like, you know what I mean? It starts slow, but by the time you hit the water, you are cooking. You completely feel all the acceleration and the dropping. You feel yourself going from slower, like when you're running and you take that like you're not really falling very quickly yet because you're going very horizontally. So you're kind of, you know what I mean? Like you got all that momentum. So at the beginning, you kind of feel like you're just almost like you're going straight, but then all of a sudden, you know, you start falling down, and then it accelerates as you hit the water. By the time you hit the water, you're going real fast towards, you know, terminal velocity or whatever, but you're not going to reach that just from cliff jumping.
No, you're not going that fast, but you're airborne by. I mean, you just do the drop calculation. You're probably airborne for 100 feet. That's substantial. You probably like three seconds or something.
I only did that 100 feet one, like I think once actually, because I did the 75 and the 60s at that particular site. I only did that tall one once, and yeah, it was crazy.
Everybody's there watching. You lose your fear. Everyone's doing it, so you're doing it too. And so, if you're by yourself, say, "Hey, jump up this cliff," and no one's watching, you're like, maybe I'll pass. That's a long way up, 100 feet. That's really high. especially if you're doing aerials. And I love watching these guys that can just jump off of a rock and just do full twisting, front flip, pike, another twist, and then boom, in a dive or even the feet.
Yeah. So why would you say there's not acceleration when you can feel it just doing cliff jumping?
What you're feeling is a change, a change of having weight to being weightless. So yeah, that you definitely feel that, and that to you becomes this. You've learned to realize that it's acceleration because you know what the consequence is. You have to be accelerating because when you hit the ground, you're freaking going, 70, 80 miles an hour when you make the contact with the ground.
You can even hear it in your ears, like the wind in your ears. At the beginning, it's like shh. By the time
you're definitely mocking through the air. I mean, there's definitely drag and there's definitely going through the air. No question about it.
that's the acceleration. It's downward. If you want to call it a force, you can, gravity, etc.
Oh, you're absolutely accelerating through the air. There's no question about it. You can feel it, measure it. You can take an anemometer in your hand and measure exactly the airspeed at which you hit the ground. Airplanes fly all the time, and they crash all the time, and we know the speed of their impacts and their airspeed indicator will definitely tell you what you're hitting the ground at. That's not the point. The point is, are you in free fall or not? Are you having any forces acting on you besides the drag?
Well, it just depends on whether you want to define it as a force or not. But I mean, weight, what you want to call gravity. I mean, it just depends on what you define it as. But definitely accelerating down towards the ground. I mean, there's just no scenario that the ground is coming up to meet you. There's just none. There's only in my view, kind of like a mind like a mind exercise way that you could think about it in that way. But it's not real physics that the Earth is moving, up towards you. You're just accelerating towards the water. Why would it be anything different? Zanick's well, when you put it like that.
No, no, I mean, I don't argue with you about it because I know we both are looking at it from two different perspectives. But I just plugged in your 100-foot, 30-meter cliff. You're hitting it 55 miles an hour, and I said 3 seconds. It's 2.5 seconds after jumping. Because mine was like 2 seconds, I think, by the time I hit the water. Yours like 2.5, 3 seconds.
It's like 0 to 60
miles an hour.
in a Porsche.
What's that?
That's like 0 to 60 in a Porsche.
Yeah, exactly. That's why, yeah. That's why they say if you were going to accelerate 0 to 60 in 3.5 seconds or something, or so 3.2, 3.4, that's like the same force of gravity pushing you in your seat. You should feel that. You feel it. You don't feel it jumping. You just feel kind of weightless.
I'm sure this has probably been asked before, but how is the Earth accelerating upwards on a globe everywhere?
Because the acceleration is not the change in speed, which is a change of velocity, which is acceleration. It's a change of direction, because direction is a component of velocity. It's a vector, the direction and a speed. And so the direction is changing, and that's the acceleration. So there's the answer. The ground doesn't have to be moving upward. You just have to be having a curved path based on the bending warping of space-time.